Hello and welcome to this poster presentation. My name is Daniel Gaviria and I will present fractional chirp-slope-shift-keying for SDR-based search and rescue applications. I would like to start by explaining the context in which this modulation scheme was designed, and it is for satellite-aided search and rescue applications. More specifically, the COSPAR-SARSAT program, which is a standard that has been around since several decades and aided the rescue of several thousands of persons. So the way it works, it is whenever there's an emergency, the distress beacon or emergency beacon sends a signal to the satellite constellation of the COSPAR-SARSAT program. This triggers a rescue mission, and the search and rescue mission looks for the location of the distress. Additionally, the emergency beacon sends a continuous homing signal over time in order to aid the location of the distress. We will focus mainly on this homing signal since we want to modulate additional communication information into it. So the main characteristics of this homing signal are following. It has to be an isotropic AM emission at the search and rescue bands, which are 121.5 MHz or 243 MHz. And the signal has to be chirped and have a bandwidth between 700 and 1300 Hz. The repetition period of the signal has to be between a quarter of a second or half a second. So in total we get this blue area in which the chirp signal should be contained. And here we have two examples of some instances of chirps that would meet these specifications. So our goal now is to modulate additional information into this signal, into these chirped signals, while still keeping these specifications from the standard. So the idea we came up with is to modulate the information into the instantaneous slope of the signal. So since we have to keep the total bandwidth and the absolute frequencies at which this signal has to be contained, we have this degree of freedom of the slope, of the instantaneous slope of the signal, in which we want to modulate a binary sequence, for instance. So, for instance, we define this binary sequence xi, and depending on its binary value, we set one slope of the different or another one, so k1 or k0, those are the slopes for the binary values, and depending on them we define the instantaneous frequency of the signal and accordingly also the instantaneous phase of the signal. And this is the way the transmit signal is created. Since we're playing around with the slope but have to keep a total bandwidth, we need to have a known amount of ones and zeros within a repetition period of the slope in order to get a constant bandwidth. And that's this condition. In order to meet this condition, we need a constant weight code. So we have the same amount of ones in a certain period of time, independently of the information bits. For instance, if we try Manchester code, we just code a 1 into 1 0 or a 0 into 0 1. And this way we have an example here of an information sequence uj, which is coded with Manchester code and the coded sequence has a constant amount of ones and zeros. This way the bandwidth condition is kept. So by doing this, we have, instead of having a perfectly linearly modulated chirp, like the blue one in this figure, we have a chirp whose slope varies in time, and we get the black one in this figure. So the system would look more or less like this. We apply the constant weight code, then modulate according to the slope-shift-keying I just presented. And then on the receiver side, we need to evaluate the difference between the linearly modulated chirp and the slope-modulated data carrying chirp. For that, we can just mix both signals and evaluate the instantaneous frequency in time domain after low-pass filtering. Then we have this kind of signal like the blue one on this figure, and we can detect, in this case we can do it by a match filter, getting the black curve, and we can decide the binary sequence at the receiver. And I will say a couple of words about synchronization in a few seconds or minutes. At the core of this modulation scheme, we have frequency estimation, since the information is finally coded in this frequency time domain. So we tried out two different methods for the estimation of the instantaneous frequency. The first one is the minimal approach with very, very low computational power and true time capability. That would be a straightforward digital phase lock loop. What this kind of system does is it just tracks the phase of the received signal through a control loop like this one, and out of that it implies a certain instantaneous frequency which we can then evaluate. Totally, the transfer function of such a system corresponds to a second order low-pass filter, and we can set the characteristics of this filter by designing the coefficients of the filter, and this way we can filter out every noise that's outside of the effectively used bandwidth for the information. So we can get rid of a lot of noise like this, and as I will show later, this leads to very good performance even at negative SNRs. The second method we tried is linear least square frequency estimation. The idea behind this method is to fit a polynomial onto the phase of the received signal, as we do with this linear equation. So we have the polynomial in here and the coefficients in this vector, and we want to solve this system in order to get the best coefficients in terms of least square difference to the measured phase vector. So the solution for that is given in this equation, and after estimating the optimal coefficients, we just need to perform a derivative with respect to time to get the instantaneous frequency given as a polynomial for a certain window. So in this approach, we take a window and estimate the polynomial that describes the instantaneous frequency and instantaneous phase the best for the given window. As I mentioned before, synchronization is also a very important part of this system, since we need both chirps to be correctly synchronized in order to evaluate the phase difference correctly, where the information is modulated. So for this kind of synchronization, we had an idea inspired by traditional FMCW radar signal processing, as you can see here. The way it works is the frequency difference between these two chirps, in this case the blue one and black one, is proportional to the delay between the both of them. Since we know the total slope of the chirp and the total repetition period, we can estimate the timing mismatch between the two of them by evaluating the instantaneous frequency of this mixed signal of the mixing product of these two chirps. And that way we get this equation for the estimate of the timing mismatch between the chirps. All right, we implemented the system and did numerical simulations for both of the presented frequency estimation methods. Here you can see the frequency estimation, the instantaneous frequency estimation by digital phase lock loop dotted, the linear least square estimation dashed, and additionally we evaluated with which BER could be theoretically achieved if we used an estimator that always meets the Kramer-Rao bound. We performed the simulations for 128 bits per second, 256, and 512 bits per second. As you can see, the performance degrades significantly depending on the bit rate. That is due to the different areas of these coded bits, different effective bit energies in the frequency time domain that depend on the duration of each of these bits. So if we do slower bits, then we have more effective bit energy in the frequency time domain. Additionally, so at the left side you can see the Manchester code as I presented it before. And additionally, we also implemented a 6B8B code which maps 6 information bits onto 8 coded bits with a constant weight of 4, Hamming weight of 4 ones per sequence. As you can see, using this 6B8B code leads to an overall performance of the curves. So at this point we have demonstrated the successful communication data transmission within the specifications of the Kospar-Zarsat standard. We have different implementations for each of the building blocks of the system. And as we can see, we get very near to the theoretical performance we would achieve at the Kramer-Rao bound for the instantaneous frequency estimation. It's worth to say, the low complexity Manchester code has the big advantage of having an easily on-the-fly detection, which we can do with a simple match filter. This means we require very low computational power, but it has degraded performance in terms of BER compared to a higher rate code like the 6B8B code. The 6B8B code has a rate of 3/4, as opposite to the 1/2 rate of the Manchester code, and this leads to a larger energy per bit effectively. So that's why it leads to a considerable improvement of the BER performance, but this comes at the cost of way higher computational power needed for the detection with a filter bank, which compares each of the possible sequences to the one estimated by the system. That would be it. As I said, this data transmission within the standard is demonstrated and is ready to be. Has already been implemented on software-defined radio and could be integrated onto commercial products for this kind of search and rescue systems. Thank you very much.